So in the past few years, in the programming language research, lots of people starting to use a database query language called Datalog to do the program analysis. And when we're doing that in my research, I find that Datalog sometimes can be very slow to run. So I'm looking to like, is there any way I can accelerate in that using the cutting edge hardware, for example, the GPUs. And today I will be presenting our journey to building such a GPU-based Datalog engines. So first, let me just give a quick introduction about the Datalog. Excuse me, give me. So Datalog is a simple language. Essentially, it only has one rule, basically. And it's written in a form called horn clause. Horn clause has two parts of it. The first part is on the right-hand side called the body of the clause. It's basically a conjunctive queries. And each of the body clause is a predicate over a database. So basically here, in the second row, if ancestor xy says, if in the table xy, in the table ancestor, I have a tuple have value x and y. And in the predicate parent means that in the parent relations tables, I have a tuple yz. And they join on the y column, the second column of the ancestor and the first column of parents. And if such join exists, I will insert a new tuple into the ancestor relations. As you might see here, different from normal database query languages like SQL, we natively support recursive queries. So for example, here, ancestor relation appear both in the head clauses and the body clauses. So here. So the classic way to evaluate a Datalog query is converting that into a relational algebra. For example, here, this iconic ancestor query can be interpreted as first rule, projection parent relation, and the second rule, do a join between parents and ancestor. Then, taking the result, use the set union back into the ancestor relation. And yes, in the Datalog, unlike in SQL, we use set-based semantic rather than the back semantics. So this allows us to do some interesting optimization I will say later. But since, as you can see here, our rule is actually recursive, so we also need to apply a fixed point operator here, which means we run the rules again and again until we cannot insert any tuples into the database, and we reach a fixed point. Okay, so set-based semantic of the Datalog allows us to evaluate the recursive rule more efficiently using an algorithm called semi-naive evaluations. So semi-naive evaluations, what it will do, it will divide each relation in the database into 3 different versions. First is the new, which is a tuple you generated from the current iterations. And the second one is delta, which is a tuple you get from the previous iteration. And the last one is full, which contains everything. And the typical evaluation workflow in single iterations works starting from you running the join, you get the result, and materialize the join results into a new version of the relations. And then you run a deduplication phases in here. You do basically anti-join between the new relation and the full relation to get the unique parts and store that into the delta relation, which will be used in the computation of next iterations. And by this way, you can massively reduce the redundant computation by only working on the unique incremental parts, the deltas. And then, in the last part, also will be very important, is that in each end of each iteration, you need to merge back of your delta back into full. So make sure in the next time you're not redoing the same works. So you might also see that in the Datalog, essentially it will be compiling into the relational algebra operators. So what is the difference from the other, for example, memory-based database engines? So the one of obvious one is that in the previous slides we have talked, an important operation is you need to merge the delta parts back into the full relation. So the indices in the database engine, in the Datalog engines, need to support the merge between 2 indices to be very fast. But typically in most of the OLAP database, for example, in the DuckDBs, like the ART, although it's very fast to be parallel build, but it's not fast to be like merge build tuning for the merge operations. And also the other, although it's different in this part, but I also want to say that many of the ideas in the database can still work in building a Datalog engines. So for example, you still need to use the iterator model to do the join processings. You still need to tune the join ordering, and you still need to think about you want to do worst case optimal join or normal binary join, tuning the variable orders. That's also still a very important part of it. Yes, so yeah, in some, as I said before, like in some of the query, the merge performance can be very important. For example, in the previous query we showed before, when you benchmark it, like 70% is actually running on the merge delta to the fulls. So why we want to migrating our Datalog engine to the GPUs? Actually, we have a strong belief that it's going to work because lots of database applications, Datalog application, they are essentially memory bounded, which means you have higher bandwidth, memory bandwidth on your system, the faster processing you could be. So, and what is the fastest bandwidth machine in the world? It's NVIDIA's GPUs. So these incredible machines have more than 4 terabytes per second bandwidth. So it's massively larger than any CPU system you can buy in the world. And also, it has more than thousands of threads in there, thousands of cores in there, and each cores have 32 bits wide SIMT processings. So you have lots of potential data parallelism opportunities. So that's why it brings us to the idea that we want to run in the Datalog on the GPUs. So our first step to making this work is, as we talked before, like different from normal GPU database you would build, like GPU Datalog engine need to fine tuning for its data structure to better fit its applications. So the first we try to build our new data structure support for the Datalog. So 2 major concerns. The first, as like database engine, we need a fast range query for the iterator operations. And the second is, like, as we talked before, we need fast index merging. And for the fastest index merging you can get on the GPU is using an algorithm called pass merge, GPU parallel pass merge. And that will require you to store all your data under the hood to be stored in a large compact arrays and a large compact continuous arrays to apply that algorithm to do that. So in our data structures, the bottom layer is still basically a large arrays. But to support index query on that, we build an extra hash table layer which, while indexing for each joined columns, what is the other unjoined columns values range inside the data arrays, like where's the offset starting and where's the size for each join prefix values. So besides that, we also insert an intermediate level here. It's not very obvious that why you don't just directly sorting the entire tuples in the database, but you sort the permutation to pointing to the data array, but I will explain the detail in the next slides. So the reason why we build this is because a huge concern in the GPU merging algorithm is that it needs to merge, unlike normal merge, it's not in-place merge. So if you want to merge the delta to the full, you need to pre-allocate a memory size, which has a size of rows in the delta plus rows in the fulls and times the arity size. So it's a large, basically it's a large memory spike, and you need to double the entire memory of the system, which gives you a lot of memory contentions. But by adding this extra permutation layer, we basically have a smaller size of array to merge. So this is good. But it also creating the fact that on your large arrays, data arrays, only the part of the data is sorted. It's a little bit like LSM tree-like structure. On your actual data is only a part of things is sorted and it's not entirely sorted. So And it will reduce to the problem like on the GPU while facing the pointer tracing and lower cache behaviors. But to mitigate that, we need to perform a compaction operations to make it resorted by after n iterations. And which is good about this is even if we do in the compaction, like each compaction still only need extra memory has a size of single column because you can do column by column gather operations. So we are not fully doubling the memory size and same as the entire relation size times the arrays. So to validate that, we're running our new database engines, Datalog engines, on a relatively large program called Polonius. It's Rust's experimental borrow checker written in the Datalog. It has around like 20 rules, so it's not huge, but it's still relatively large. So the performance is actually pretty good. Like if you look into it, for some very dense operations, the dense means that you only have few less than 1,000 iterations to run, but you generate a huge output database. And in these cases, you can accelerate the result by even 100 times speed up. That was due to both the fact that GPU has higher bandwidth, also due to the fact that you have lots of threads to explore the data level, instruction level parallelisms. But it's not always very good. It very much depending on the things. There's that in the parallel computation, you can't just get for free. Your work needs to be able to parallels. For example, some benchmark shows that if your work is really sequential, like need a few thousand iterations to run, there's just no hope to get this working just by applying this. But you can still get some accelerations. Like here, our benchmark shows you still can have like 7 times speed up in that, which is very good. So after we explored the data structure of the Datalog, and we further need to think about like, is there any other problem we're trying to solve? So what immediately brought up to our research group is a classic problem in the database. Like you want to store your data in the row fashion, or you want to store your data in the column fashions. So in our research, we found that actually you always want to store on the GPU's data log setting. You always want to store your things in the column-oriented fashion. Here's why. So on the GPU, it's a faster machine, but it has the strong restrictions. Is that you want to have running in full speed, you have to make each thread on its course accessing the contiguous memory at the same times. But if you store your relation in the row-oriented fashion, you are very likely to hit into the cases that when the relation is wide, you have multiple arrays, each thread will be accessing the non-contiguous memory. But if you do that in the row column-oriented fashion, it's better to follow this coalescing memory access patterns. And another important reason that we try to use the column, we favor more column-oriented version on the GPU Datalog, is that most of GPU primitives, like hash probing, the sorting, and the merge operation we have mentioned before, they only have good performance when you're handling the data support atomic operations. So it means that basically you cannot make your things larger than the size of U64 if you want to atomically swap them. So yeah, this is an oversimplified version because we didn't mention like a lot of detail about how you actually implement the column-oriented way on the GPUs. For example, you might want to use a PAX or whatever tricks you want to do. But here it's just a simply illustration, like try to convey the idea that why the column-oriented way is better fit for here. So we also compare like what if you apply the column-oriented way comparing with the traditional row-oriented way. So the result is showing on the figure here. It's almost like in every case, column-oriented storage is faster. And you can get average by like 2.5 times faster than you just store things on the rows. So after I built build this Datalog basic block for the primitives, for the relational algebra operators. I get some critique from the research community says that, oh no, you're just building primitives, you're building basic block, but you're not building the real Datalog. So what does that mean? Why they have such kind of critique? Because like in the Datalog engine, unlike database, the query can be very complex. And this is a typical query I extracted from a famous programming analysis framework called DUP. And this is just randomly selected, almost all rows like in this fashion. So you have very deep pipeline, which means you have often more than 4 relations to be joined together at the same time. And you can see the join pattern is also very complicated. Like invocation columns will be joined across 3 different relations, and 2 methods will be joined from the last 2 relations. So it's kind of a mess, and you need to perform smart scheduling between them, and you also need your machine. You also need your engines to have ability to really handle them. So our current ongoing work and our answer to this question is we try to apply in the iterator model-based processing, which has been very mature in the database community for past 20 years. So, but there's a difference if we want to do on the GPUs. In the traditional database, like if you are doing the parallel working on the iterator model, you will typically boot 1 thread per iterator for the outermost relation in the left deepmost planning. So for example, here you may be for this joins on the Y column. I'm using worst case optimal join as an example, but the binary join should also work in a similar way. Like you boot a thread for each unique Y and creating the pipeline, doing the join, assemble the query, and compiling your query into this kind of CPP code. But this creates a tension on the GPU too. One of the problems is I said before, like on the GPU, we usually favor a coalescing memory access patterns. But if you boot a one threads per row fashion or 1 thread per value fashion, during the join, when you search on the second relations, you are actually accessing 2 very remote parts of your memory address. So for example, here you see on the left we join on the value Y, but on the other relation, value T threads accessing 0 might be at position 0, but T2 accessing 1, it could be very far away at position 7. So this is the reason 1 why you might not want use a single thread per value way to parallel and creating the iterator models. The other important reason is that it's not even supported in most of GPU's libraries. Most of GPU libraries, they don't provide the primitives for operating on the threads, but instead they provide the primitives operating on the entire warp. This is because GPU's threads is fundamentally different from the CPU threads. It's essentially just SIMT length, not the real threads mapping to the cores. So that's why most of this GPU library is not providing a threads-based accessing library. Although I know some GPU-based database do still use this way, and they heavily hack their data structure to allow that. But honestly, I don't think that, but it must fit in their cases, but not fits in when you try to do that on the Datalog cases. So on the Datalog, what we do is we use the warp per value sessions. So we boot 32 threads work together on the outermost value 0 at 1 times. And the benefits of this is we can still use this 32 work collaboratively to working on the scans and on the hash probing. Also work on, even on the binary search, you still can benefit from this 32 threads grouped way to do the search, but you are working on a more memory coalescing access pattern, and you can reuse what has been standardized in the GPU libraries, for example, Q collections from NVIDIA and also lots of library, like if you want to use cuDiff also use this kind of ways to do it. So, but there's also sometimes you do need to divide it 32 lanes working on 32 different things at the same time to do what we call instruction level parallelism in the GPU programming. That's the parts when you want to materialize your join result. So in our engines, the compiled query, when we materialize the result, we will redivide the work inside the same verb to let each thread working on writing different memory addresses for the results, for the join results. So in this way, we can fully utilize the memory controller benefit from the GPU to do what they call instruction level parallelism. So here's the overall infrastructure graph of our new Datalog engines we propose, and we are heavily working on it. So it has three main different parts. So the first is the query compiler, which essentially doing is we compile the query, compile Datalog query into relational algebra operators, and we also build the iterator model-based pipelining for the processings, and that's purely done by that's purely done by macro expansions. So the benefits of macro expansion instead of just raw compiling is that you can insert any kind of CPP code natively into your code. So it gets kind of like seamless deduction versus like pure compile language based way. And the medium parts of our things is that we also build a template library to helping you writing the relational algebra much more easily. So this idea is coming from, like in the AI community, they build tools to help writing, to use the CPP template metaprogramming to do the relational algebra operation, and we just steal the idea from them. So which are also building in this way to make the engine more configurable. Like you can change in the template arguments in your code to change the data structure you use, changing the join algorithm you use, changing the join order heuristic you try to see there. And the last part is we also provide a core library for providing different data structures. As you've seen before, on the different query, you might use some customized data structure to do that. And we're also providing that and allow you to combine it with template metaprogramming library. You can configure what kind of data structure you try to use. Yeah, that's basically today's talk. Hopefully you enjoy it. If you have questions, please go ahead.
Yeah, you could go back to the slide that was like the benchmark table. It's like Polonius something. It'll be a while.
Yeah, sorry.
No worries.
I should turn off the.
Oh yeah, I just didn't actually understand what you were measuring here. Like, yeah.
Oh, it's raw running time speed.
So what? Yeah, you could just explain very.
Okay. So we compare in our work with the state-of-art Datalog solver called Soufflés, and we're running the Soufflés on a 32 cores CPUs, and full 32 cores is in working. So it's parallel building. And for example, for some benchmark, the first benchmark, Soufflé took 122 seconds to finish the Polonius queries on the clap RS database, which is a data set you're extracting from the raster compiler. Raster compiler has a flag. You can export the data from when you're compiling it and running it in the Datalog engines. So we're also doing that, but just changing the query engine from the Soufflé to our own engine, and we see like more than 100 times speed up in some cases, some input cases.
Okay, thank you.
Thank you.
On that slide, what are you mentioned what Soufflé is, but what are VFlog, NeMo, and RD5?
Oh, so VFlog is our engines in this case, is our GPU engine, and NeMo is another Datalog engines, but mainly used for symbolic AI applications. And RD4 is also another Datalog engines used for also for the RDF settings, but they have more restriction. For example, they only allow like 2 array relations like that. It's also a very interesting tool, but it's commercial tools.
Did you benchmark against like Cairo, or does Cairo just send it to a Datalog?
Oh.
Sorry, no, I say Cargo, sorry.
Yeah, this is like the input thing. So Cairo means we're running the Rust compiler on Cairo that code base, and the Rust compiler will generate the inputs for the borrow checkers.
But I'm saying like Cargo is running. There's a borrow checker somewhere. I'm guessing it's not a Datalog engine. I'm guessing that like it's just using a normal, probably Rust implemented borrow checker or something. Did you benchmark against that?
Yeah. So I didn't benchmark against the raw one, but yeah, they do run in the Datalog engines for that. They have their own Datalog engine called DataFrog, but it's very limited. It's very, very limited feature, even more limited than RDForks. So it's not a general Datalog engine.
Yeah, this is, I see. Mm-hmm. And then when they were saying that, when they were critiquing you by saying that this was a too simple Datalog query, does this mean that basically the Rust borrow checker is kind of a simple, like the rules are not super recursive or the joins are not too crazy? Or?
Yeah, the first I would think about is like it's only 20 rules.
I see.
So 20 rules is relatively still very small in the Datalog queries. Like dupe, if you look into the code, it has like more than 3,000 lines of code in the Datalog. And DDisasm, which is a Datalog-based disassembler, high-precision disassembler, that will cost maybe like 10,000 lines of code. That's a lot of code. So we are still doing in scale relatively small. So I think it's very valuable critique to my work.
I see.
So it seems like your research, you're mainly focusing on running in the batch context like Souffle.
Yes. Yeah, mainly on the batch context, but on the incremental setting, usually it won't be very good.
Your experience run at a scale of a single GPU, or is this a GPU cluster?
Oh, so this work, particularly in the benchmark, is running on a single GPU. But we also, in our group, we also have my colleague working on expanding that into multiple GPUs. We have a paper in ICS this year talking about this.
Is it not a thing for Datalog implementations to have like alternative backends? Like, could you have done this work as an alternative backend to some existing Datalog engine, rather than it seems like you built your whole entire new Datalog?
The problem is that on the CUDA, like you have to compile the things into the GPU kernels, but most of the Datalog implementation, they are compiling things into, for example, CPPs. Like in the Souffles, you're compiling into raw CPPs. It's not the CUDA you can directly get in from there. And also, as I showed in my slides, the iterated model, accessing of the iterated model also change a lot once you do that. So that's why we choose to like writing the full infrastructure in our own in-house stuff.
Does that also mean that no existing Datalog implementation could easily provide an alternative backend for a GPU?
Yes, no.
Okay.
It is a very basic question. Just thinking Datalog versus SQL. I think at least they're kind of equivalent. All of these queries like dupe or the rest, whatever, that could probably just be written with CTEs in SQL. Why are people using Datalog? You mentioned, I think in the beginning, it was maybe the bag versus multi-set versus set. I don't think you followed up on that. I'm just curious, like, why Datalog?
Yeah, so first, like even if you use CTEs, like, for example, in DuckDB or Umbra, they do support like a recursive query, but they don't support mutual recursive. So it only works on very simple cases recursive query, but for the real Datalog application, it really can't support that.
Okay, I don't really know what that means, but I've heard like stratify and recursive or something in Datalog. That's,
yes. Basically, we also try like running things for example, on the DuckDB. One of the reasons it's not directly working is like DuckDB doesn't support the merge operation that good. So, but that's kind of one of the most crucial workload in here. So that's why, that's also the reason why most of Datalog engine doesn't directly use the existing database and the backend.
I see. So Datalog and SQL are equivalent at the language level, but if you look at the implementations, like the Datalog backends are kind of more powerful in a sense because they have full recursion or something.
Yeah, also it's more like Datalog query is just easier to read. Sometimes it's also an important reason. Yeah.